Okay, so now we're getting on to types of identities, and this is sort of the first step in the algebraic proving of identities that we're going to be doing quite a bit of further in this unit. First of all, we have the tan x equals sine x over cos x, and we have the reciprocal of this, that cot x equals cos x over sine x. Now, one thing that's very, very important is you'll notice, since we've put the cos x in the denominator here, and the sine x in the denominator there, we have that cos x can't equal 0, and that sine x cannot equal 0 respectively. That's going to come into play when we look at the NPVs of this. Now, my reciprocal identities, and we've already talked about these. Cosecant is 1 over sine, secant is 1 over cos, and cotan is 1 over tan, or subsequently cos over sine. We have that sine x cannot equal 0 here, cos x cannot equal 0 here, and then sine x and cos x cannot equal 0 there. Now, some of you guys may look at this and be like, well, here we say the cot x simply just cannot, or for the cot x, the sine x cannot be 0. But here, for cot x, I'm saying sine x and cos x can't be 0. We don't have a contradiction there. It all has to do with how we're presented with cot x. If you are presented with just cot x, then it's the sine x cannot equal 0. But if the question is presented as 1 over tan x, then we have that sine x and cos x cannot equal 0. So it just depends on how the question is presented to you. I assure you it will not be an issue going forward, though. When we're doing the proving, all the questions will be very clear. Now from here, we have the Pythagorean identities. And this all comes down to the whole equation of the circle, where you have x squared plus y squared equals r squared. Well, from before, we had x is cos and we had y is sine. So, also, our radius was 1 because it's a unit circle. So that gives us this wonderful identity of cos squared x plus sine squared x equals 1. If you ever want a really, really cheesy math pickup line, you have walk up to the person that catches your eye and be your cos squared, I'm sine squared, together we're 1. I assure you it will work some of the time. Now, very, very importantly, you guys will be given this one on the formula sheet, but you are also responsible for the manipulations of them. So moving the sine x over to the other side and getting 1 minus sine squared x, or moving the cos squared x to the other side and getting that one. If we divide both sides of the equation, oops, didn't mean to strike that out, but if we divide both sides of the equation by cos squared x, then we will also get that 1 plus tan squared x equals sec squared x. And if we divide both sides by sine squared x, we will get cotan squared x plus 1 equals cosecant squared x. Now again, you guys will be responsible for the manipulations of those. Just keep that in mind. So with my, I'll do this in black. So with my tan squared x, it would also equal sec squared x minus 1. Or if I moved the tan squared x over, I'd get sec squared x minus tan squared x equals 1. Subsequently here, I could get the cotan squared x equals cosecant squared x minus 1. Or if I move the cotan squared over, I get cosecant squared x minus cotan squared x equals 1. Okay? Now we can use these identities to rewrite and simplify trig, solve trig equations, or we can use it to prove other identities, which we will get to in a bit. Now the first question that we're going to look at comes down to the non-permissible values again. So when we're looking at these non-permissible values, well, where do these not exist? So tan, if you guys remember from before, for our tan, we said that cos x cannot equal 0. So all I need to do is figure out where is cos x equal to 0. And cos x is equal to 0 when x equals negative pi by 2, pi by 2, 3 pi by 2, and forever and ever and ever in both directions. So if I wanted to put this in a general form as to all the places, you notice that from pi by 2 to 3 pi by 2, I add pi. For the next one, I'd add pi. And then going backwards, we just minus pi. So we'd get that x cannot equal pi by 2 plus n pi, or all those instances where we've added pi. Now here, again, we remember that n is in the set of integers. Sorry, I double struck that. And you can write the set of integers as either being an I or a Z. For my next one, we have cos x all over 1 minus tan squared x. So in this case, it all comes down to the denominator. The denominator cannot be 0. So I go 1 minus tan squared x, and we say that can't be 0. So tan squared x cannot be equal to 1. Or tan x cannot be equal to plus or minus 1. So we check out all the cases where tan x cannot be equal to plus or minus 1. And this is one where, again, we go back to our unit circle and we look at our unit circle for all the cases. And what we notice is that x cannot be equal to pi by 4. And then after that, every pi by 2, we get another solution. So we go pi n by 2, because that's where all of the next solutions would occur. And then again, we say where n is in the set of integers. Now, for my next one, where we have sec x over tan x. This one actually comes loaded with quite a bit. So I'd have that tan x cannot equal 0. As well, for my sec, it would come with the fact that cos x cannot equal. So what we'd end up getting, because again, remember that my sec is preloaded as 1 over cos, so that would tell me that my cos x cannot equal 0. So now what this tells me is that both sin x cannot equal 0, nor can cos x equal 0. Well, where is sine equal to 0? And sine is equal to 0 at 0, pi, 2 pi, and forever and ever and ever in both directions. Where is cos x equal to 0? Well, cos x is equal to 0 at pi by 2, 3 pi by 2, 5 pi by 2, and again forever and ever and ever in both directions. So if I wanted to combine these two solutions, well, we equal 0 at 0, pi by 2, pi, 3 pi by 2, 2 pi, 5 pi by 2, and so on and so forth, forever in both directions. So my solution for this would be x does not equal the pi by 2, and then we multiply that by the n, and then we say where n is in the set of integers. That'll be good for this lesson. We will move on to more NPVs in the next one.